before we dive in, this is an introduction to Effect cluster, so I'm assuming you already know Effect. If you don't, check out Practical Effect, my course that covers all the foundations. Link in the description. Before we write any Effect cluster, we need to talk about actors. Effect cluster is built on the actor model, and if you skip this, I'm sure the API will feel a little bit arbitrary. Why do entities have mailboxes? Why all this message passing, etc. We will get to Effect cluster, but first actors. So you learn to program sequentially. You write x is equal to 5 and x is 5. You call process order, it runs, it returns. Something breaks, well, you simply add a log statement, you reproduce the input, you trace the execution, etc. On a single server with a single database, this works well, and transactions are your friends. So you would say begin transaction, we check the inventory, we decrement the inventory, we create the order record, and finally we commit. And if anything fails, everything rolls back, no partial state, and life is very simple. But the problem starts when you have two or more sources of truth. So for example, your app with your database isn't two sources of truth. The app is typically stateless. It delegates all persistence to the database. If the app crashes mid-transaction, well, the database rolls back. There's no partial state. The database is ultimately the single authority. But what if you add another authority? So maybe Redis or caching or Stripe or SendGrid. You might have a perfectly ACID compliant Postgres database, but if you add another authority, can you have a single transaction that spans both? No, each system has its own transaction boundary. If you write to Postgres and then Redis fails, you can't automatically roll back Postgres. And this isn't a Postgres or Redis or whatever limitation, it's simply fundamental. Transactions do not compose across independent authorities. So for example, user signs up, so creator account in Postgres, and then we send a welcome email via SendGrid. That's two authorities you cannot wrap in a single transaction. What if SendGrid accepts the request, but you crash before recording that it succeeded? Or what if SendGrid fails after Postgres commits? So just use a database transaction stops being the answer the moment you have more than one source of truth. Now, sequential logic isn't necessarily the problem. Scale is. So if you have a single server with a single database, it will handle concurrency fine. Logs work, transactions work, the requests arrive at once, while the database serializes them, one waits for the other, and there are no race conditions. The sequential model you learned is valid, it just stops working when you can't fit everything on one machine. So what if you kept that model, but scaled it across systems? So let's say that you're scaling horizontally. So you have server 1, you have server 2, and server 3. You can't rely on in-memory mutexes, of course. Each one will have independent mutexes. So what you could do is create a single authority for your domain. So for example, a server for your inventory. So this is your inventory server, and all inventory operations go through here. Other servers cannot touch inventory directly. They need to go through this server. Now this works because the inventory server is the single point of serialization. Every request to check or modify inventory flows through it. There is no distributed coordination needed. There is only one coordinator. But it has two serious limitations. The first one is single point of failure. So what if the inventory server dies? Now what? Well, all order servers are blocked. No inventory operations happens anywhere until it comes back up. And two, performance bottleneck. So new flash sale or Black Friday and you get 10,000 orders per second and they all funnel through one server, and now this server becomes your ceiling. Now there's a third problem, and that is granularity. One server handling all inventory is too all-encompassing. Someone buying headphones has nothing to do with someone buying a laptop. With a single inventory server, they all compete for the same queue. So the singleton pattern has the right idea, single point of authority, but the wrong granularity. So if you look at your business domain, what are the natural units? Well, you have users. Each user has their own profile, preferences, balance, and so on. You have orders, so they have their own status, line items, payment state, etc. And let's say we have products. So each SKU has its own inventory count, price, availability. And these are your entities, the nouns in your business logic, and they are naturally independent. So users 1, 2, 3 balance has nothing to do with users 4, 5, 6 balance. And order 7, 8, 9 status has nothing to do with order 7, 9, 0 status. So instead of one server handling all users, what if each user had its own authority? So this, we would have user 1, 2, 3 authorities, we would have user 4, 5, 6, and so on, and same with orders. Each type plus key pair has exactly one authority somewhere in the system. User 1, 2, 3 does not compete with user 4, 5, 6. They run independently in parallel. So same benefits as the singleton pattern, no distributed coordination for a single entity without the bottleneck. Entities are independent. Now, entities need their own authority. What does that look like in practice? Well, a single server worked because it had processing, so logic to handle requests. It had storage, state that persists across requests, and communication, ability to receive requests and send responses. And this right here is an actor. An actor is a single server shrunk down to entity size. So each entity gets its own tiny server, processing, storage, and communication. And the actor isn't a new abstraction. Same architecture that worked for a single server, but applied to each business entity. So user 1, 2, 3 gets an actor, order 7, 8, 9 gets an actor, and each one is a miniature singleton with complete authority over its own state. Now, why bundle storage with processing? You've probably been taught to separate these. Stateless services over here, database over there, your code runs in containers, doesn't hold onto anything, and Postgres is ultimately the source of truth. And that separation creates a gap you have to cross on every operation. So you have to fetch. Your code cannot decide anything until it pulls current state from the database. You have race conditions. While you're processing, someone else might change that state. And you have to commit. You push your result back, hoping you're not overriding their work. And actors flip this around. The data lives in a variable in local memory. So reading takes nanoseconds, not milliseconds. But wait a moment. The data has to live in a database eventually. Power goes out, RAM is wiped, so yes, there's still a database. The difference is the life cycle. Your typical stateless service has amnesia, of course. Request comes in, you fetch state from the database, you do work, you write back, and you forget everything. Next request, fetch again, and so on and so forth. So every operation pays the latency tax. Actors are long-lived. An actor isn't spun up for a single request. It sticks around to represent that entity for as long as it's active. So when request 1 arrives for user 1, 2, 3, we check, is the actor or user 1, 2, 3 in memory? Well, at the very start, no. So we spawn the actor. So actor loads state from database, and let's say we know that the balance is 500. Then we process the request or the message. We update the local variable, and now balance is 600. Then we persist to database for safety, but actor stays alive in RAM. So you pay the database cost once at startup. Requests 2 through 1 million run at memory speed. And because actors process one message at a time, there is no need for locks. Nothing else can touch your state while you're working with it. Now, I know what you might be thinking. One actor per entity sounds expensive, but it's not. Actors are just small objects in memory. You do not create 10. You create millions. One per user, one per order, one per shopping cart, one per device. They are lightweight enough that this is practical, not theoretical. Now, most actor systems use a two-part identifier. You have the entity type, which answers what kind of actor is this. So bank account, shopping cart, user session, and then you have the key, which answers which specific instance. So again, user 123, order 456, etc. Now, user 123 might have multiple actors, a bank account, and a shopping cart. So the entity type is what determines who you're talking to. Now, of course, sometimes a simple ID isn't enough. A multi-tenant SaaS application might need tenant ID plus invoice ID, or a game server match ID plus player ID. So the key can be whatever uniquely identifies the actor instance within its type. Now, when your code says, I need to talk to the bank account for user 123, something has to turn that into an address. And this is what actor frameworks handle for you. When you ask for bank account user 123, the framework checks if that actor exists somewhere in the cluster. If yes, it gives you the address. If no, it creates the actor, possibly on a different machine, and give you the address. Now, your code doesn't manage actor lifecycles or track which machine hosts which actor. Ask for an actor by type plus key, get an address you can send messages to. Now, how do actors find each other? Well, in a single process, you just call methods. So you got a reference to an object, well, call a method on it. So for example, account.withdraw 100. But this obviously breaks in a distributed system because this account might be on a different machine, or on a machine that just crashed, currently waking up somewhere else, or migrating from server A to server B because A was overloaded. So you can't hold a direct memory reference to something that keeps moving around. So actors use addresses. An address is a handle that lets you send messages to an actor without knowing where it physically lives. In Effect cluster, addresses are based on identity, as we already know. We have the entity type, so bank account, and we have the business ID. So we have user 123, and that's enough. You send a message and the cluster figures out where that actor lives and routes it. If the actor isn't in memory, the cluster wakes it up. Actors are effectively always there, waiting. Now, under the hood, it's a little bit more nuanced because the framework needs to maintain a structured address comprised of not only the entity type and the key, but also a shard ID. So what's a shard and where do actors actually run? Well, for this, we need to start with a runner. A runner is one instance of your application code executing. You wrote a server application and the code sitting on disk doesn't do anything. When you run it, that running process is a runner. So for example, on your laptop during development, you open up a terminal, you type bourne server.ts and the process starts. shards. So of course it needs to use your computer's CPU and memory to execute your code, listen for the requests, handle the messages, etc. And that process is a runner. So imagine in production, you deploy to AWS. You might have 3 EC2 instances, each running your server, so 3 runners, or perhaps 10 Docker containers in ECS. So now you have 10 runners, or 20 pods in Kubernetes. So you have 20 runners. So each container or instance runs its own copy of your application. And again, each one is a runner. But now that we have multiple runners, we need to coordinate them so that they act as a single system. So let's say that we have 5 runners across 5 machines. Without coordination, they are just 5 independent servers. Each handles whatever requests hit it. User shopping cart might live on runner A memory, but their next request goes to runner B because a load balancer sent it there. And runner B has no idea what's in their cart. So for that, we need a cluster where runners communicate to, agree on who handles which users or entities, forward requests to the right runner, detect when a runner crashes and reassign its work, and add new runners without downtime. Now in Effect cluster, how do they coordinate? Well, coordination happens through a shared database, like Postgres. Each runner registers itself. I'm alive, here's my ID, here's how to reach me, and the database is the source of truth for cluster membership and work assignments. Now runners check in periodically, so a heartbeat, and if a runner stops checking in because it crashed, lost power, whatever, other runners will eventually notice, and after about 35 seconds, they conclude it's dead and will take over its work. And this is why Effect cluster requires a database. It stores the membership and work assignments. The database is ultimately the coordination backbone, and this right here is done by a shard. So what is a shard? Well, let's say you have, again, 5 runners, physical nodes, and millions of entities, users, shopping carts, game sessions. Each entity needs exactly 1 runner. How do you decide which runner handles which entity? The naive approach is to track every entity directly in a giant table. So user 1 goes to node A, user 2 node C, and so on and so forth, where the last one goes to node B. And this creates 2 massive problems. The first one is memory. You need millions of rows in your routing table. And 2, volatility. What happens if node B crashes? Well, you now have to update hundreds of thousands of rows instantly to move its users to other nodes, which for starters is slow and worst of all, error prone. So for this, we have shards, in that we have a new layer of indirection, where instead of mapping entities directly to volatile nodes, you map them over to a shard, and a shard is just a number. For example, 0 to 300. It is a permanent logical bucket that will never change. So with shards, routing now happens in 2 steps. The first step is hashing. So here we would do a hash user 1 and we get back shard 42, and then hash and then user 10, and this goes to shard 42, where for a given key it will always belong to the same shard, meaning user 1 will always belong to shard 42. It is stable. And the second step is assigning logical shards to physical nodes. So here we would have shard 42 to node A, and then shard 187 to node C. So we now only need to track 300 shards, not millions of users. But what happens when a node crashes? Well, if node C crashes, this shard will not die. It will still exist. After all, remember, it's just a logical bucket. So the cluster will reassign shard 187 to a healthy node. So let's say node A. But what happens to the messages? Well, for this, we need to take a look at the message lifecycle. So the normal case where the runner is alive, first the client sends message to entity user1. So we hash user1, we get shard 42, and now runner A owns it. Now runner A receives the message and runner A writes to the cluster messages table, and then runner A delivers to the actor, spawning if needed. Then the actor processes and runner A writes back the reply. And now the message is marked as processed because it has a reply. But in the case there's a failover, so the failover case, runner dies, the client sends message to entity user1, we hash it, again we get shard 42, runner A was the owner, but it's dead. So the message is written to the cluster messages table. Then after the timeout, which is 35 seconds, let's say that the cluster assigns shard 42 to runner B. And so now runner B queries for cluster messages where shard ID is 42 and there's no reply, otherwise it is already processed. And then runner B replaces those messages to the newly spawned actors. And of course we resume. So this is another reason Effect cluster requires a database. It's the buffer for messages during failover. Now for a given entity type plus key, again we have exactly one actor instance in the entire cluster, not one per machine, one total. So what happens when you send a message to an actor that's already busy? Well, your message will wait in a mailbox, and a mailbox is a queue. So once the actor finishes the current message, it will pick up the next one from the mailbox, processes it, and picks up the next, and so on. Now from the caller's perspective, your request just takes longer when the actor is busy. So you send a message, you wait, and you get a response. Don't know or care how many other messages were ahead of you. And again, the core concurrency guarantee is that no matter how many requests arrive simultaneously, the actor processes them one at a time. There are no locks in your code, no race conditions, no someone else changed the data while I was reading it. However, in Effect cluster, you can configure the concurrency. So you can have a concurrency of 10, for example, if your actor allows that. Keep in mind the default is 1, so sequential. Now what can an actor do? Well, when an actor receives a message, it can do 3 things. The first one is send messages, so to other actors, using their entity type plus ID. 2, update its own state for the next message. And 3, return a response to the caller. And that's it. Again, no direct function calls to other actors, no shared memory. You just offer messages to queues. Now, one thing you will not do is explicitly create actors. In Effect cluster, again, you do not create actors. You send messages to entity IDs. If that entity isn't running, the cluster spins it up to handle your message. And this is sometimes called virtual actors or lazy activation. So actors appear when needed and disappear when idle. You never manage the life cycle. But what if an actor needs a response. So let's say we have actor A, and this one sends a message to actor B, but it needs the result to continue. Now if A waits for B's response, A is blocked. It cannot process other messages. But now let's say actor B needs something from C, but actor C needs something from actor A. So now we have a deadlock. A sends requests to B, blocks waiting. B sends requests to C, blocks waiting. C sends requests to A, blocks waiting. And now A can't process C's request because it is still blocked on B. And now everyone is stuck. So what you can do here is, instead of waiting, A sends a message to B and immediately finishes the current message. And A tells B, when you have the result, send it back to me. So the result arrives later as a new message, and A never blocks. And this is sometimes referred to as the continuation pattern. Split your work into before and after messages. So A never blocks, B's response is just another message in A's mailbox, and A can handle other messages normally. So you basically need to store, say, in memory, all of the requests you are expecting answers from. But what if A crashes while waiting? So let's say A's pending requests are in memory. The crash wipes memory, A restarts with no idea it ever asked B anything. So once B sends a message, A cannot find the pending request, so it drops it. So for most interactions, what you can do here is let it fail. But if you have critical workflows where some processes cannot be dropped, so for example, you charged the credit card, so you must provision the account, you can't rely on memory, then you need to persist the step. So basically, the actor now has its own state machine, and for each step, it is going to persist it somewhere. That way, if you crash at any point, you replay the journal and you resume from the last recorded step. As simple as that. Now, remember the problem from the start? Reserve inventory, create an order, charge the card, and send the email for authorities, and no transaction spans them. So what do you do when step 3 fails? Well, you do not roll back, you compensate. So a rollback undoes work as if it never happened, but that's impossible across independent systems, as we have learned. Stripe doesn't know about your inventory database, and your email provider doesn't care about your orders table. There's no coordinator that can atomically undo all of them. So compensation is different. Each step has a corresponding undo action. So for the case of reserving the inventory, the compensation is releasing the inventory. For creating an order, canceling the order, charging a card, refunding the card. But what about send email? Well, there's none. You can't unsend a sent email. So when step 3 fails, maybe the card was declined, you run compensations for steps 1 and 2. So you release the inventory and then you cancel the order, and the system returns to a consistent state. And this is sometimes called a saga, a sequence of local transactions, each with a compensating action. And the journal tracks which step succeeded and their results, not just step 1 completed, but step 1 completed with this reservation ID. You need that result to compensate. You can't release inventory without knowing which reservation to release, nor can you refund a charge without the charge ID. So on failure, you run compensations in reverse, and on crash, you replay the journal and continue, either forward or compensating, depending on where you are. But there are some key differences. Sagas from database transactions. And that is 1, there's no isolation. So Sagas are atomic, all or nothing via compensation, but they are not isolated, meaning that other actors can see your work in progress. So someone might observe reserved inventory before the order exists. So you need to design accordingly. 2, compensations are real operations. So a refund isn't undo the charge. It's now a new charge, but in the opposite direction. So it will show up, for example, in the customer statement. And 3, some actions can't be compensated. So again, you can't unsend an email. So the idea here is to put irreversible actions last, after everything that can fail. Once you start an irreversible step, you are committed to finishing. If it fails, you retry until it succeeds. So forward recovery. There is no turning back here. And lastly, compensations can fail too. So the refund API might be down. You need retry logic, which means compensations must be idempotent. If refund card runs twice due to a retry, it should not refund twice. And this is the most common mistake when implementing Sagas. And sometimes automation isn't enough. Maybe the Saga can suspend itself, record where it got stuck, and wait for a human to fix the problem manually and then resume it. So this is the trade-off. Database transactions give you atomicity and isolation, but they do not cross boundaries. Sagas cross boundaries and preserve atomicity, but sacrifice isolation. So for most real-world workflows involving external services, Sagas are perhaps the only option. Now I want to expand more on step 3. Some actions can't be compensated. So that's the point of no return, where you know that, again, some steps cannot be undone. Send email is a classic example, but there is a better one, and that is buying something non-refundable from a supplier. So let's say that you're building a system that sells digital gift cards, so Xbox, PlayStation Store credit, whatever. So your workflow would look something like this. First, you charge the user, so you take $50 from their credit card, then you acquire the code, so you call the Sony or Microsoft API to generate an activation code, so it costs you $48, non-refundable, and lastly, you deliver the code, so you show it on screen or email it. So what happens if step 3 fails? Maybe the email bounces. If you compensate backward, compensate step 2, you can't, the API is non-refundable, you own this code now, and then compensate step 1, you refund the user $50. So what would happen then? Well, the user has their money back, you paid $48 for a code you cannot sell, and you lost $48. So this is why step ordering matters. Step 2 is your point of no return. Once you pass it, compensation is not an option. You are committed. Now, when delivery fails, you do not refund. You retry. You send the email again, show an alert in the user's dashboard, notify customer support. You keep trying until you deliver what they paid for. And this is forward recovery. So to minimize risk, again, you should order your steps the right way. And that is first, all of the compensatable steps. So things easy to undo, reserve inventory, verify address. Then 2, you have the pivot step. And this one is high risk, which is the irreversible action. You charge the card, you buy the non-refundable item. And 3, you have the retryable steps. Things that can run 1,000 times without side effects. So sending emails, updating analytics, grant badge, etc. Now we have been assuming messages are persisted, written to the database, replayed on crash. If a runner dies mid-processing, the message gets delivered again when a new runner takes over. Your handler might run twice for the same message, so it needs to handle that check. Did I already process these before doing work? But Effect Cluster also supports volatile messages, which is for fire and forget, no persistence. If the recipient crashes before processing, the message is gone. So obviously it's faster, no database query, but there are no guarantees. So use Volatile for disposable operations like hash updates and logging, and use persisted for anything that matters. So payments, state changes, etc. Okay, this now wraps up the video. With this, you should have all of the foundational knowledge to start using Effect Cluster. So make sure to be on the lookout for the hands-on practical video. If you want to see more content like this, make sure to subscribe. I'll see you in the next one. See ya.